You just wait for a few more minutes to see if someone joins and then you begin. Let's begin. So we'll go over the questions of week 3 assignment and then some other practice questions that will help you when we go through week 4 assignment questions. So we'll start with week 3 assignment questions. Before that, somebody had asked yesterday for the equations, the cheat sheet or some sheet where all the equations are there. So this was there, I think, in week 1 and week 2 slides. So I just put up all the equations together, I think 3 slides. And this should help us solve all the questions that are there in at least till week 3. Okay. So first we had discussed the static stability and what it means with regard to an aircraft. Then we had discussed what aerodynamic center is. So aerodynamic center is the point about which the pitching moment is independent of angle of attack. For the entire aircraft, it is the neutral point. Aerodynamic center, neutral point are the same thing. Aerodynamic center is for the wing, and the aerodynamic center of the entire aircraft is the neutral point. Okay. Then we had the pitching moment equation, that is Cm is Cm naught dCm by d alpha into alpha. So this is the linearized expression for the pitching moment coefficient. Then we had contributions from wing and tail. So we had done this extensively in yesterday's question, the one that I had posted in week 2 and we had solved yesterday. So the wing and the tail contribution, this was individual components of these equations were used to solve these questions. So the wing and tail contribution, this is the Cm naught contribution of the wing. This is the Cm naught contribution of the tail. So it contributes towards Cm naught, that is the intercept, y-intercept. It doesn't contribute towards stability. What contributes towards stability is the Cm alpha components. So this is Cm alpha wing, and this is Cm alpha tail. So these two components contribute towards the stability of the aircraft. So we can see that the wing contribution is positive, and so it is destabilizing in nature. And the tail contribution has a negative sign, and the entire term is negative, so it is stabilizing in nature. Because for stability, we require Cm alpha to be less than 0. All right. So neutral point we have already discussed. Then is the neutral point equation. So we had done this derivation again, I think week 2, and it's also there available in the lectures. Then we had discussed static margin. Static margin is like a quantitative measurement of the stability of the aircraft. So it is defined as the negative of the slope of Cm versus Cl, and also the distance between the neutral point and the CG. All right, so static margin for a stable aircraft is always positive, because for a stable aircraft, dCm upon dCl will be negative. All right. Then we had these set of equations that will help us get the individual terms of the wing and the tail contribution. So epsilon naught and d epsilon by d alpha give you the downwash. Downwash, the linearized term is epsilon naught plus d epsilon by d alpha into alpha of the wing. So this epsilon naught and d epsilon by d alpha, they're given by the equations, this one and this one. And what we need to make sure here in all of these equations that the units are either radians or per radians according to whatever the parameter is. So it has to be in radians or per radians. Then you have the expression for horizontal tail volume ratio, St upon S by into Lt upon C bar. Lt is the tail moment arm. Tail moment arm is the distance between the aerodynamic center of the tail and the CG. So this moment arm is what contributes towards the stability, or what provides the restoring moment that the tail is offering. Then you have a relation between the CL alpha that is provided by an airfoil and what the wing actually delivers. So when the airfoil is made into a wing of finite span, then there is an intersection of flows at the tips, and then it doesn't give you as much CL as the airfoil properties tell us. So the relation between CL alpha 3D and CL alpha 2D, that is the CL alpha given by the wing and the airfoil respectively, is given here. This again is valid only if the units are per radians. Okay. Then the next set of equations pertain to control. So we have started with the longitudinal dynamic control. So here what control does is that it does not affect stability in any manner. So deflecting the control surfaces do not affect stability, do not change stability at all. What does it do? It kind of translates the Cm versus Cl graph. What does this help us with? It helps us in trimming the aircraft at different CL values. So the slope of the graph, so it remains, if this is your Cm versus Cl, and you deflect control surfaces, The slope remains same. What changes is the y-intercept. So this is CM versus CL or CM versus alpha. They both follow the same pattern. They both have negative slope for stable aircrafts. And upon deflecting the control surfaces, this graph translates, maintaining the slope. So it doesn't change the stability. It only changes the CM naught value. So you can trim your aircrafts at different CLs. The conventions that we discussed were elevator down is positive. And what this does is effectively changes the camber of the tail, hence giving you a greater lift. Okay. The equations that we saw was CL delta E and CM delta E. We can see CL delta is positive and CM delta is negative. This we had done this question yesterday. So we know why CL delta is. If you deflect the elevator down, which is considered positive deflection, there is a positive change in lift. And this positive change in lift leads to a nose down or negative pitching moment. This is why these terms have the positive and negative sign respectively. Then we have the control surface effectiveness parameter, tau, that is d alpha t by d delta E. This again we had seen yesterday, varying definitions of it, varying properties. Then we had seen delta E trim, that is how much you need to deflect your elevator to trim at different CL trims. All right, so in this equation, you plug in the different values and you will be able to do it. This again is a equation of a negative slope. So delta E required CL, they have such a pattern. So as you move the CG closer to the neutral point, it keeps reducing the slope until at the neutral point, it becomes zero slope, as you can see from this term. Okay. So this is just a quick recap to have an idea of all the formula that we will use. Okay, so now we'll go over the contents of questions of week 3 assignment. So this was the data given to us for a series of questions, and they've also given us some useful formulae making our lives easier. So the first question is the lift coefficient for cruise is. What was cruise? Cruise was one of the equilibrium conditions or trim conditions where you have lift equal to weight and thrust equal to drag. So what we can do here is that the weight that is given to us, we can assume a lift equal to weight and then find out the CL. So how do we find out CL? The equation for lift was
half rho v squared CL.
yes,
SCL.
SCL, correct. And from there you can get CL is 2. Instead of lift, you can take W. So 2W by rho v squared S. When you substitute the terms, you get the answer. So yeah, this is the equation here. When you substitute it, you get it as 0.51. The next question was to find out the downwash angle. This again, we had done the same thing last class, but the difference was that there we had CL not given to us directly. Here what we have alpha at 0 lift. So I just draw the graph. That is the lift curve's slope. So this is the lift CL versus alpha curve for the given F1. And the alpha at 0 lift, that is this point, is minus 2.3 degrees. And they've also given you the slope. So that is in per radians. The alpha at 0 lift is in degrees. So we need to ensure that conversion. So how do we find out CL naught from here? This is CL naught. The CL naught is 0 minus 2.3 into the slope. It's just that. So it's 4.664. And that is in per radian. So we just have to divide this by 57.3. Okay. And then you plug in this value over here. And then it's fairly straightforward. Aspect ratio is given to you. Pi is given. E is given as 1. Aspect ratio should be, yes, aspect ratio is also given. So you just plug in the values and you will get the answer. Okay. Next question was value of CM naught tail. This again, that is the CM naught contribution of the tail. That was the first part of the equation. The tail contribution, the first part of that. So I've just written it down here. VH is, we have given as 0.52. Eta is given to us as 0.88. CL alpha tail in per radians is 4.664. And you have your angles in degrees. So conversion is necessary here. So 2.5 plus epsilon naught Not, I think it was 1.21. 21 minus of minus 8.4. And then we have to divide it by the whole divided by 57.3. So you get a value of 0.227. Here. Next was the value of CM naught of the entire aircraft. So we found out the CM naught contribution of the tail, and they asked us to assume the fuselage contribution to be 0. Then the only thing remaining is the CM naught contribution of the wing. So we need to find out CM naught contribution of the wing, which is given by this formula. Again, the first part of the wing contribution equation. So CM alpha, CM AC of the wing, that is of the airfoil, those characteristics. So that is given to us. CM AC.
Minus 0.16.
Yes, so it's given us minus 0.16 plus CL naught into X bar CG minus X bar AC. But in the question, X bar CG and X bar AC are
The same.
point, so it is just 0. So it's just 0.16, and so CL naught of the entire thing is minus 0.16 plus the CL naught contribution of the tail 0.227. You get 6. Then a CM delta E, which is the direct substitution of the formula. You have eta is given to you, VH is given, CL alpha tail is given, tau is also given. So you just substitute it directly, you should be able to get it. That is fairly straightforward. It's minus 0.8956. Static margin is just the difference between the neutral point and the CG. So neutral point and CG both are given to you. This is the CG, this is the neutral point. So it's just 0.55 minus 0.34, which comes to 0.21. Now, so all of these terms will be, all of these quantities will be used to find out this delta E required. Delta E required formula was, so this is focus on this. Delta E trim is given by this formula, where this is the, this is the y-intercept and this is the slope. So all of these terms we have found out. CM naught of the entire aircraft was, I think, 0.0679. CM delta E we have, so it is 8956. We found it out in the previous questions. Then X bar NP minus X bar CG, the previous question gave us 0.21. CM delta E is same. And CL trim is the first thing that we solved. So that is 0.51. And this gives us an overall of 0.09. So yeah, that is also straightforward. Okay. Here they've asked us to find the elevator control power in per radians. So elevator control power is nothing but DCM upon D delta E or CM delta E. So basically they've asked us to find out CM delta E. So it's just to find the slope. So DCM by D delta E, that is 0.025 minus 0.079 by 0.07 minus 0.53. This gives us the slope as 0.09. Right. This is not the point. You can just get the required answer. Stall velocity of an aircraft increases as height increases. True, false, no effect, cannot stay. So the formula for Vstall was under root 2W by S by rho CL max. So given all the other terms to be the same, only if the height increases. When the height increases, your density decreases. This term decreases. So height increases, density decreases, and hence Vstall also increases. So it is true, as the height increases, Vstall also increases. Okay. Now we'll just do some questions, general questions that will help you with the other assignments. So lift is perpendicular to thrust, free stream velocity, fuselage reference line, or chord line. So these are the two aerodynamic forces that we know. So lift and drag, they are perpendicular and parallel 2. If I have,
Chord.
no. So if I have, so if this is my airfoil and this is my chord line, and then you have an angle of attack. Angle of attack is with respect to
Free stream.
so alpha. And then you have your lift and drag generated perpendicular and parallel to your free stream velocity.
Okay.
Just a minute. I think it should be called. Okay, yeah, it should be called. Let me just look at that. Just- But, no, I still think it should be free stream velocity because the lift and drag change accordingly. So yeah, it's perpendicular to the free stream velocity. So lift and drag. I'll just draw it clearly. It's free stream velocity. Okay. Which type of propeller configuration gives less longitudinal stability of the aircraft? Pusher, tractor, both options are correct, or you cannot say. So, do you know what pusher and tractor configurations of propeller are? Let me just draw it. So, if this is your fuselage reference line, and say this is your CG, the tractor configuration of propeller,
Front propeller.
yes, front. So, this is tractor,
Vector.
and this is pusher. So these propellers are the ones that produce the thrust and then hence the lift and the drag. So can you try to see which of them will be more or less longitudinally stable? Which configuration would be more or less stable?
Pusher will be less stable
Tell me why?
because the flow first comes, airflow first comes to the nose where where the propeller is.
But in terms of pitch dynamics, so longitudinal stability. So for that, we had seen restoring moments and all that, right? So can you try to think in terms of the moments, the pitching moment? So say it is the aircraft is subject to a gust and then it moves upwards. Which configuration will try to bring it back to equilibrium? So when it is subject to a gust, your disturbing moment is in this direction. So if it is a stable configuration, your restoring moment should be in the opposite direction. This is the disturbance. So let's just take each of those cases. So the tractor configuration generates the lift here, right? And here, so let's just say that's L1 and the pusher generates lift here. So due to L1, you have a further destabilizing moment. So if it is subject to a disturbance and it's a tractor type configuration, you don't have any restoring moment. The moment produced by the tractor is further destabilizing. But in the case of pusher, you have this L2, which creates a restoring moment. So because of this, there is a restoring moment at the CG and the aircraft tends to come back to its equilibrium position by pitching down. So in this comparison, the pusher is more stable. So the question was which gives less longitudinal stability, and that is tractor. Next question. In an aircraft, size of the elevator is decreased, keeping the vertical tail volume ratio constant. How will this affect the longitudinal stability of the aircraft? Okay, it should not be vertical tail, it should be horizontal tail. So the size of the elevator is decreased, keeping the horizontal tail volume ratio constant. This is VH. How will this affect the longitudinal stability of the aircraft? Just try to see that. Just look at the equations for CM and just see the CM alpha terms and see if you can get some hints.
Remains same.
So it remains same. So our this was the tail contribution equation, and there you don't, and you just have to look at this part. So this is your CM alpha contribution of the tail, which is the only term that contributes towards stability. Here, the size of the elevator does not feature anywhere in the equation. So nothing to do with the control surface affects the stability. So when they say that the size of the elevator is decreased, but the vertical tail volume ratio or horizontal tail volume ratio is remaining constant, then nothing in this term changes, and hence the stability remains the same. The static longitudinal stability of an airplane is provided by vertical tail volume ratio, horizontal tail volume ratio, both vertical and horizontal, none of these. We just discussed this horizontal tail volume ratio. The position of neutral point of an aircraft is 0.5 meters from the leading edge of the wing. And the location of center of gravity of the aircraft is 0.4 meters from the leading edge. The location of aerodynamic center of the aircraft from wing leading edge in meters will be.
0.1.
How did you come up to that? So let's try drawing it. This is supposed to reference line. This is the wing. So this is this. This is the middle point. So this is 0.4 meters. This is 5 meters. CG. middle point. Now the trick here is that they've asked you the location of aerodynamic center of the aircraft. So aerodynamic center of the aircraft is nothing but the neutral point, right? So both of them have the same definition. Aerodynamic center of the aircraft is the neutral point. So it's just 0.5 meters. So it's just, that was a tricky part of the question. If they had asked aerodynamic center of the wing, then you would need other terms to find out. You can't just do it. This would be the aerodynamic center of the wing. So it's usually 1/4 from the leading edge, 1/4 of the chord length from the leading edge. Yep, that is generally the location of the aerodynamic center of the airfoil. But here they've asked you aerodynamic center of the aircraft, which is the neutral point. Okay. Yeah. In the flight measurement of neutral point, at neutral point, which of these quantities
One
are-
question here.
Yes.
The aerodynamic center and neutral point both are the same.
Aerodynamic center of the aircraft is the neutral point.
Okay.
So we have aerodynamic center. The definition is where pitching moment is
Independent of the angle of attack.
Yeah. Neutral point definition is also the same thing. So when they say aerodynamic center of maybe wing or tail specifically, then it is of those aerodynamic surfaces. But when they say aerodynamic center of the aircraft, it is the neutral point. That it is by definition, that is what neutral point is.
Okay.
So in flight measurement of neutral point, at neutral point, which of these relations hold true? D delta E trim by DCL trim, is it 0, positive, negative, or you cannot say? At neutral point. This is D delta E trim. I don't think it's written correctly. So our notation is D delta E trim. So delta E trim by DCL trim.
First one.
So this was the graph. So I had just drawn this as the CG moves closer to the neutral point, the slope keeps decreasing, and at neutral point, it is 0. So this is D delta E trim. So yes, that's the first one. This is at neutral point. Now, some data is given to us for a series of questions. For an aircraft, the tail area is 1/4 of the wing area, and distance between the two aerodynamic centers is equal to half of the wingspan. Wing and tail are in rectangular shape, and you have the following data. So you have CL alpha of the wing and tail, alpha at 0 lift, the mean aerodynamic chord, span, CM AC of the wing, tail efficiency factor, CM AC of the tail, the distance between XCG and XAC, the wing setting angle, tail setting angle. So let's look at the questions. The pitching moment coefficient at 0° angle of attack of the wing will be Cm naught contribution of the wing. Let's try doing this. Formula for Cm naught of the wing. Try doing it.
minus 0.009 last.
So try doing this. CMAC wing. CMAC wing is minus 0.009. CL naught, we'll have to find out data given to us. So CL versus alpha. This is alpha at 0 lift, that is -2. We need to find out CL naught. CL naught is it's just 0 minus 2 into the slope. CL alpha, it's given directly in degrees. So 0.9, it's just 0.09, sorry. It is 0.18. So you can do 0.18 xCG minus xAC wave. So that is given as 0.03. To solve this, you get minus 0.0036. So that is the right answer. 0.003 minus 0.0036. Okay. Next is the CM alpha contribution of the wing. So there I don't have the formula. This should be just direct substitution. So it asks you in per radians, so you have to multiply 57.3. So substitute this 0.7, 57.3. So we can see the CM alpha wing here is positive. It means that the wing is not contributing towards the stability, it is destabilizing in nature. So we do need a tail to give you the restoring moment. Right. Next is the value of downwash angle epsilon naught. It should be epsilon naught at 5-degree angle of attack. Try to solve this. The formula for epsilon naught is this. We can just try finding on both epsilon naught and the slope. I think for this, you'll have to first find out the aspect ratio squared by S, and then you can proceed with the terms.
For a rectangular wing, no?
Yes.
One, it will be no? Both.
1, 2, 2, so B squared by S would be S would be B into C, right? So this will be B into B by B into C, it will be B by C. It will not be 1. Span we have as 26. 26, where C bar is 2.2. This would be the value. If I want you to find the entire downward triangle, not just epsilon, the whole thing. So we have to find out these two and then just by doing this. This is 3, CL naught was 1 to it. Using since the value is given in degrees, let's just convert this to degrees. 7.3. Just calculate it. For the slope along similar lines, what will the slope be? So the slope along the similar lines. You just pick 2. To see alpha y is 0.09. If it is in per degrees, then this equation will not be valid. So we need to convert it. So 3 by 5 is 1, is 26. 2. We get 0.2778. Now they've asked you for the entire downward angle. So it is naught plus the epsilon by d alpha into alpha. Epsilon naught is 0.555 plus 0.2778 into alpha is 5 degrees. So this comes to 1.94. And the option favor mistake, but it should be that. It comes to 1.94. Are you getting the same thing? Are you getting 1.19? Let me just try doing this again.
No.
I think there's something wrong with the options. It's 1.94. Next, the pitching moment coefficient at 0 degree angle of attack for the tail. CM naught contribution of the tail. This is the equation. You've been able to do it. So I think we have to start with VH. SPS VP upon C bar. SP upon S is 1/4. LP upon C bar is LP into D. B by 2. C bar. Now it's just a direct substitution. What would the answer be? CM contribution of the tape. The fixed stability derivative of the tail in per radians is the equation. fuselage contribution to CM alpha is equal to 0.99 per reading. The difference between neutral point and aerodynamic center of the aircraft in meter would be. So formula for neutral point. So quantity and so the average table. With this, we combine with today's questions. So if you have no further, if you have questions, please ask me. And if you have no further questions, we'll meet again next week.
See, I will go through all these problems, and I'll get back to you if I have any questions.
Sure. Okay. You can also put it up on the forum, or we can discuss this next week.
Okay.
Thank you.
Hmm. Thank you.